Bismillahirrahmanirrahim. Assalamualaikum and very good morning. Can you hear me?
Waalaikumsalam. Can I
Waalaikumsalam.
can.
Yes, can.
Good morning, doctor. Yes, can hear you.
Morning, everybody. Okay, good morning Sunday with very nice weather outside. Right. Okay, so we continue our discussions, our lecture on the chapter 1, still on the introduction of the system ID, application of models, how we want to tackle the models. So we continue with chapter 1E. So chapter 1 consists of 3 documents, chapter 1, chapter 1A, and chapter 1B. All are supported by book chapter that I attached in the WhatsApp list. So there is a concept of identifiability, okay? Kebolehan untuk mengenal pasti, okay? In Malay. So ability to identify a unique model for a given system depends on the 3 critical aspects. Okay, the first one is the the model itself. First critical aspect is the model. We must know the property of the model. Exists a unique mapping between the model and the parameters being estimated. Unique is the one and only one. Okay, so it cannot be carbon copied or more than one solution of model and so on. That is the meaning of unique. And then it comes to the condition, the protocol, the procedure of the experimental. So that matters. What to do first, what to do next, what to do later, and so on. This will include a type of input and sampling rate, the most influential and significant. Because when we choose a wrong input signal to be applied to the system, unknown system that we test. So the type of input is matters. The sampling rate that we choose is matters. So we have to go to the configuration or the setup of the frequency sampling. Okay, so how many hertz, how many kilohertz you want to sample? We cannot undersample, too low frequency sampling. Okay, and so to be safe, people choose 1 kilohertz, or in other word, sampling time is equal to 1 over sampling frequency, which is equal to 1 millisecond. 1 millisecond in sampling time is equivalent to 1 kilohertz sampling frequency. So input must be generated as requisite information required to distinguish between the 2 candidate models, which is the real one and the estimated one. So the estimation method also play an important critical aspect. Okay, the coefficient that we try to identify, to evaluate the value of the coefficients. Okay, a number of methods are available. So many methods. If you go to the journals, if you go to the conference, so many methods are available for parameter estimations. And the method must be capable of estimating the true parameters. Okay, if finite samples are available, which is termed as an asymptotic property of the estimator, which known as a consistency. Meaning that when we try this method, see the coefficient first, we get the first solution of the coefficients. Then we try another one for the second time. The coefficient is not far different from the first one that we get. Okay. So I'll give you an example. Okay, so in this example, you are given y is equal to k theta equal to theta 1, theta 2, uk, where theta 1, okay, is the parameter that under identifications. U is the input, okay, while y is the output, okay. So theta consists of theta 1 and theta 2, okay. K is the sequence, Okay, is the sequence number, start from 0, 1, 2, 3, 4, and so on. So to given data where UK and YK are the input and output of the system, so theta is equal to theta 1, theta 2, which is the power of T, capital T, meaning that is a transpose, transpose sign. Transpose meaning we interchange the row become vector. Okay, so this one is considered as a row matrix, and this one is considered as a column matrix. Okay, so is the parameter vector to be identified, which is theta. So the prediction, okay, the estimation, the prediction or the approximations is usually denoted by head. Okay, denoted by head. Okay, so if there is no head, just y, this one is meaning the actual. Okay, the real one, the actual. But when there is a denoted by y hat or y cat, so this model is estimated. So y estimated in terms of sequence k and theta is equal to theta 1, theta 2, uk. So regardless of the input, two different parameters value, which is theta 1 and theta 2, produce identical predictions, which is can be statically mathematics in this term, okay, where theta 1 is equal to theta 2. So therefore, the mapping from the parameters space to the model predictions, okay, between the real and the predictions is not one-to-one. So formally, the model is not globally identifiable. Consequently, it is not possible to arrive a unique estimate of theta because theta is always changing, especially in dynamic systems or dynamic process. Okay, so on the other hand, if the model is reparameterized in terms of the single parameters, which is beta is equal to theta 1 and theta 2, then the model is identifiable at all points in the beta space. If you look, we have a static process and dynamic process. So dynamic process include DC motor rotation, AC motor rotation, something that involve linear actuator, pneumatic, and hydraulics that is moving. So this one is considered as dynamics, and the parameter is always changing during parameter estimation. Compared to the static process is something that do with the process control, which have a tank located at that side, stated at that side, is not moving. Okay, the tank is not moving, but the level of water is going up and going down. So that we consider as a static process. So this is the detail of the example 2.1, which is available in the book chapter. So here I summarize it. Okay, summarize it, and you can read more details in the book chapter that given. So the second example is consider a linear time invariant system governed by the following input-output relationship, which is a third-order finite impulse response system. So in this case, this is a sample of FIR. FIR meaning finite impulse response system. This is a sample of it, where yk is equal to b1 uk minus 1 plus b2 uk minus 2 plus b3 uk minus 3. So you can see that it is until 3. So this is the highest order of the FIR, which is a third order. So with B1 is equal to 1, B2 is equal to 0.6, and B3 is equal to 0.3. So we considered sinusoidal input of the sinusoidal input as the input. So meaning that U is the sinusoidal, okay, U is the input, Y is the output, B1, B2, and B3 is the coefficient given as 1, 0.6, and 0.3. So the sine wave, the input is equal to sine 2 pi 0.1 k, which is equal to sine omega naught k is applied to the system. So omega naught is equal to 2 pi multiplied by 0.1. So you have to derive the output of the system. So under the input, okay, this is the equation. So we replace each U by UK. So sine 2 pi 0.1 K equal to sine omega naught K. So we insert inside here UK minus 1 as omega K minus sine, UK minus 2 as omega naught K minus 2 sine, and UK minus 3 you replace with the sine omega naught K minus 3 sine. So therefore, when we simplify this YK, so it will become B1 plus B2 over 2 cos sine omega naught K minus psi, and plus B3 plus B2 over 2 cos sine omega naught K minus 3 psi. So if you open this sign, you can derive back the equation back as methods. The issue now is the simplifications. We have 3 terms here. So we simplify it, become 2 terms, which is this one and this one, more simplified. And then we simplify it again by B1 prime sine omega K minus psi, and B3 prime as sine omega naught K minus 3 psi. Thus, we have a 3-parameter model that is manifest as a 2-parameter model when viewed through the lens of the monofrequency input. But unfortunately, it's not possible to uniquely recover B1, B2, B3 from B1 prime and B2, B3 prime. So we have to observe that we can rewrite the previous equation of the pair sine omega naught K minus psi and omega K minus 2 psi, or you can write it as omega naught K minus 2 psi and minus 3 psi power of cubic. Okay, so therefore it's a matter of simplifications. As long as when we open the simplification, you can get the equation back. Okay, and the important thing is the parameters B1, B2, and B3 can be estimated uniquely. So the further details, you can refer to the example 2 in the book chapter attached in the WhatsApp. So in system ID protocol, we cannot avoid from a noise. Okay, as I told you before, noise can come from many sources. The common sources of the noise probably come from the, for example, the 3-pin power plug. Okay, a 3-pin power plug in the lab or in the house is the source of noise of 50 Hz. It also can come from a condition unit, okay, which are available in the house and in the office or in the lab when we taking a data. And it can comes from a handphone, okay, since handphone is a microwave device, so it also can generate some noise that enter to the process or to the input or to the output of the system. So what is the relation between the noise and the signals? It is simply the formula is given by variance of signal divided by variance of noise. Is a ratio, okay? Is a ratio. That's why we call it as a signal to noise ratio, or standard form as SNR. So the term signal here is the true response, the signals that we want in voltage. And the noise is the mix, the uncertainty that enter to the process, either in input and output, and join the signal as well. So the problem now is how we can ignore SNR and how we cannot ignore this SNR. It depends on the value of the noise. It depends on the value of the ratio here. So if the signal to noise ratio is high meaning big value, okay, the ratio is high, so this is considered good because your signals is more dominant, is more significant compared to the noise. But if your signal to noise ratio is low, so this is not good, okay, this is not good, and you lost your informations, okay. That's why you have to cater this issue of noise, okay, because the SNR represent the ratio of effect due to the known variables versus the uncertainties. The lower of the SNR, the more ambiguous is the estimate of the input and output of the model. of the model. So we look at the two samples here, the effect of SNR on the parameter estimations. So we want to see the relation between the output Y and the input U. Okay. So it's related by these equations. Okay. Yk is equal to B1 UK plus B0. It is a first order system. Okay. Because you have only one input and one output, plus the polynomial is given by B1 is equal to 5 and B0 is equal to 2. So we conduct the experiment. Okay, we conduct the experiment by two conditions. First is the signal to noise ratio is 100. Second one is the signal to noise ratio is equal to 10. Okay, so we have two types of SNR. We look on the left where the cross sign legend here is the data. So you have lots of data here. Okay, the output and the input together we captured, so we plot it. And the straight line is the best fit that fit the data that been given. So if you still remember, this is the equation of Y is equal to mx plus c. Okay, where this is Y, this is x, and this is c, the intercept. Okay, and m is the slope of the curve fitting, right? So when the SNR 100, we observe that the best fit line, the estimated or the simulation or the approximation straight line curve is fit very well to the data given by the legend of X. Okay, but if you look to the right, where the signal noise ratio is equal to 10, so the data start to tabulate not accordingly to the proposed estimated line, right? So the data is everywhere from this quadrant, okay, is far away from the best fit line that we propose. Although we are using the same equation, which is Y is equal to mx plus c, is the linear equations, okay? So in this case, we go back to the statistics where we see the coefficients of the B1 and B0. Okay, so it's given here, B1 equal to 5 and B0 equal to 2. So for each data, we see that the standard deviations during SNR equal to 100 is 0.036 for B1 and 0.02 for B0. Okay, surprisingly, is the right one, which is SNR, is equal to 10. You can see that the standard deviation is getting bigger compared to the left one. So for B1, the standard deviation is 0.114 and the standard deviation for B0 is 0.064. So the conclusion, the best fitting is SNR 100, where you can see that with the lower standard deviations. So we can see that the best linear fit and the parameter estimate two different settings, which is SNR equal to sigma y square divided by sigma v square, namely as SNR 100 and SNR 10 that we obtain from 200 samples of data. Okay, 200 samples, right? So we have a 200 sample for the output and for the input. So data are shown in figure 2.1a and 2.1b. Then the quantities of B1 hat and sigma standard deviation are the estimates and the standard errors. If in the estimates of B1, I is equal to 0, 1, and so on. But the estimate do not vary significantly with the change of SNR. But the errors for BI and sigma BI, okay, is the estimate increase roughly by a factor of 3, okay, between the SNR 100 and SNR 10. So this will give us theoretically, which is signal noise ratio 100 divided by 10, so it's equal about 3. 3 times difference, okay, three times compare between the left and right figures. So look again, so you can see that the 3 times different between the left and right data. So in practice, SNR, even though it's not priori, but it's always a factor that the tester and the designer always lose about it. So therefore, SNR issue is play an important role in estimation exercise. Okay. So the second issue is the on top of SNR is the overfitting. So overfitting meaning that we fit the data, the best straight line or the best curve, estimation curve. We always overfitting, meaning we over quote the model as a higher model. So when the system is third order, okay, the data is captured from the third order system. Okay, the real system is third order. Sometimes we fit the third order with a very higher order system. For example, power of 6, power of 7. So it means that higher order actually didn't fit. It's not the best solution for the system ID. In a matter of fact, that the 7 order or 6 order can be simplified, and this is occurred due to the fact that the system has been overfitting. Okay, macam kita beli baju lah, kita punya badan kecil, size M, kita beli satu size atas sikit, iaitu L. So orang yang badan L, badan dia large, dia takkan beli yang size S atau size M. Itu adalah underfitting. So usually dia akan beli satu lagi step, which is XL, supaya dia lebih comfort. So kalau kita pilih 3XL for those yang size L, so kita katakan dia sebagai overfitting. Baju tu jadi jadi macam tak sesuai dan dia overfitting, tidak sesuai dan terlalu besar. So same case to the model where overfitting is always happen. Okay, sometimes the researcher just use the software without knowing what is the software calculate in terms of error, in terms of training data, in terms of model parameters. So it produce a poor predictions, okay, on the data set. And sometimes it causes the system become unstable for the estimation model. For example, the input and output data here is shown here, okay? So you have captured the input data, you capture the output data and you capture the input data. So now the data has been plotted, okay? It looks like exponential curve, right? By looking at it, it looks like an exponential curve. So visual inspection reveals that polynomial can capture the relationship reasonably well. Okay, so therefore, in order to choose the appropriate order of the polynomial for that curve, so we use a sum squared error of residual. Okay, which is drafted against the order of the polynomial shown in figure 2.2b. So this is the residual normal. Okay. Then this is the order of the system. So you can see that at order 1, the residual normal is very high, 25. When it goes to 2, so there is a big jump between 2 and 1. Okay. So residuals 25 plus for 1. This one is about 4.5 for order 2. And starting at 3, so the residual become more constant. Okay, dia menjadi lebih flat and mantap. So until 4, 5, 6, 7. So maintain at 2.5. So this is the best order that can fit to the exponent graph shown just now. So the problem now, whether you want to choose 3, 4, 5, 6, or 7. So what choice that you have? A good choice of the order is 3. Okay, the best is 3 because it is the beginning of the residual become consistent or constant. Since the improvement in the residual norm at higher orders is minus scale, meaning that it become more stable at 2.5. So it would be useful to know that if the third order is indeed the optimal choice, so this cannot be determined using the training data alone. So a test data set is also required to assess its predictive abilities. We call it as the procedure of cross validations. So this is the data that we shown previously, and this is the norm of residues versus polynomial order fit. So we feed it with the third order, okay, exponent, fourth order exponent, and fifth order exponent. You can see that the third order can fit the data very well compared to the fourth order and to the fifth order by using another function, which is a cross validation of polynomial models. So it is clear that third order polynomial model offers the best compromise, okay, between 1, 2, 4, 5, and 6 in the predictions or the training and test data. So the fitted polynomial, the predictor, is where the values in brackets are the standard errors in the coefficients of the estimate. So we propose the estimated model is third order with the difference equations shown here. Okay, 1.183, 0.384 UK, 0.314 U square K, and 0.19 U3 square. So the numbers given here is the tolerance error that occurred for each of the coefficients, which is B0, B1, B2, and B3. Okay, so it is almost 0 at plus minus 0.0374 and 007. So it is useful to compare the estimated model with the true model, okay, for data generation, where VK is an ideal random noise. So we assume a noise enter to the system and we set as 10. Okay, and see what happened next, okay, whether the system agree or not with the order. The fourth and the fifth order models can be ignored, even though it give a lower residual norms, okay, on the training data. Okay, so you can see the fifth order cannot fit the test data very well. Okay, so the reason for the poor performance of the higher order model is that they have attempted to explain the chance of variations using the same input. So that's why cross-validation play an important role for the final decisions of the choosing data. Okay. So you can see that the graph again, okay, at 3 compared to 4, 3 or 4 also can, but the best is the 3 to fit the given data. With the equations, this one is for the fourth order, okay. It's not much different from the third order. The third order until U3, but the fourth order also can be fit, but due to the high order, so we always choose parsimonious model concept, where we have a lower order system with the quality model representations. So over parameterizations has to be viewed not with the reference to the true model, but respect to the model that can be identified. So for two reasons. First is the process is usually much more complicated, okay, than the model being fit. Then the second is the number of parameters and order of the model that can be estimated, largely governed by the input expectations. So issue of overfitting must be catered similar to the signal to noise ratio. So we must avoid higher order model because higher order model will represent complicated structures, okay, and complicated analysis. So let's go to the one example in the journey of identifications in the, what do you call that, overview, when you have a system until you get the final model of the representation system. So usually this is the simple one, schematic of a liquid level system, where we have a single tank, and we have those who are in the industry very familiar with this is the control valve, okay, is a valve, okay, that have a door, right? So the door can be controlled, okay. So this is the, what do you call it, the flow, okay. So the door can be controlled to close 100%, to open 50%, or to open 10%, and so on. It can be done by manually, it can be done by automatically. And this is the input flow. Input and output flow. Okay. And we have a level. Okay. And suppose there is a sensor for it. Okay. Sensor. So anybody can give a suggestion for sensor levels? Any sensor levels? No, I'm just talking, so maybe you can give two-way communications with me. Anybody?
Water level sensor.
Lah, water level sensor tu specific name dia apa? Capacitance sensor, okay. What else?
IR sensor.
Infrared. Infrared, no. Jarang pakai. Yang commonly used. What else?
Floating sensor.
Sorry, floating. Floating is a mechanical lah.
Mechanical.
Mechanical kan. So itu yang dekat tandas lah, dekat toilet tu kan. Tangki toilet tu, floating, ataupun dekat tangki rumah. What else? This is mechanical, this one is electrical. Conductor sensor. Conductor sensor. Okay, so dia ada dua tu. So once the water touch this one and touch this one, so it's conducted, so the water will stop pumping, right? What else? Tanya pelajar-pelajar ni, dia banyak industrial experience. Anything? Fariza, senyapnya? Ultrasonic. Okay. Okay. What else? So you can think by yourself, okay, and by reading the books. Okay, so many sensors available. So single tank always referred as a first order system. Okay, it's namely known first order system. If you have a second tank, let's say you have a second tank here beside the first tank, so the system become third order system. Or you have a 3 tank connected like this. Okay. So the water jump here, the water jump here. Okay, water jump here and water jump here. So this is a third order system. Okay, so it depends on the number of tank in that particular system. So in this journey of modeling, we will see on the physical process, data generation, models for simulation, input used for data generation, data visualizations, and preliminary analysis, building a non-parametric model, building on parametric models, goodness of the models in terms of prediction, in terms of tests for deterministic model, tests for the noise, cross-validation, final model, and then developing a state space model or a transfer function model. So the process of interest is a buffer system. We call it a buffer system or a tank system. Okay, shown in the figure 2.4, consists of cylindrical tank. Okay, cylindrical tank is the tank bulat with the inlet, with the outlet, flow rates of input Fi and F0. So the unit is meter cubic per hour, meaning that the input flow and the output flow are measured based on volume in 1 hour. Okay, so 1 hour consists of 60 minutes. So 60 minutes consists of 3060 seconds, okay, respectively. So the objective is to build a model that explain the changes level in HT with respect to the changes in the flow rate FIT. So the end use of this model could be in simulations, control, and monitoring of the liquid level system. Okay, so usually you want to control the flow rate and the levels, okay, H and Fi, and then you want to monitor the liquid level system. This one more towards chemical engineering. So the first principle, okay, first principle models based on the law of the liquid level system, okay, is the conservation of mass, which is the d per dt ht plus 1 over AC CV square root ht equal to 1 over AC FIT, where H is the level, okay. AC is the cross-section area of the tank, okay. So cross-section ni apa? Luas dia. If this is a radius, so the cross-section will be pi r square. CV is the valve coefficients of the outlet. So this one is must refer to the product, the manual that come with the control valve. Okay, so there is a valve coefficients at the outlet, or the keluaran. So the quantity AC is the cross-section area. Okay, H is the level again, multiplied by 1 over area, and then the input flow in meter cubic per hour. So during experiment, we must have assumptions. Apa assumptions yang kita pakai? Kita tak boleh tak ada assumption, because bila kita ada assumptions, kita memudahkan kerja kita untuk derive the mathematical model. The first assumption is the fluid incompressible. Okay, incompressible, that's the first assumptions. The second assumption is the outlet flow rate being proportional to the square root of the pressure head, which is the valve equation. F0 is equal to CV square root HT. Okay, so we must have assumptions in order to do the to derive the model. Okay, and then with the operating condition set to the Fi 4.5 cubic feet, okay, cubic feet per minute. CV is equal to 1.5 and AC is equal to 0.5 foot square. The nominal level is equal to 9 feet. Okay. So the input used for this simulation is discrete time pseudo random binary sequence, or PRBS. Pseudo, P random, R B binary, and S is signals, which consists of short and long duration pulses switching between the two levels around the nominal operating value. So the PRBS input has a certain advantage over other inputs, okay, which will be discussed in chapter 2. So the profile of the PRBS is shown here. Okay, so this is the sample of PRBS signals, which is flow versus samples. We inject the signals to the input of the system. The long duration pulse in low frequency secure the gain information, while not so long one are useful in capturing the dynamics of the process. So after we inject the input, okay, so this is the input, we obtain the output, which is the level, okay. So the input we inject to the flow, the valve, okay, and the input control valve, and then the output is shown here. You can see that the output try to follow the PRBS as good as possible, okay. So level versus samples, and flow versus the samples. And then when we plot the spectra, the input and output spectra over here, okay. And this is the power spectrum of PRBS, and this is the power spectrum of the output of the system, okay. So basically kita kata dia sebagai in decibel lah, decibel versus frequency. So the response of the sample data, ZOH process sampler, is obtained by numerically integrating the nonlinear ODE, ordinary differential equation, which is here, okay. So from time t equal to 0 to t2045, and observing at ts equal to 1 minute sampling intervals. So simulation is using in the MATLAB. So we use these equations, okay, in the simulations. You can see that the sampling time is 1 minute, very, very slow, huh? Very slow. Every 60 seconds, one sample, one sample, one sample, one sample. So the interval is 60 seconds, okay. Tak payah beli yang mahal-mahal lah. Beli yang murah-murah punya data logger. Okay, yang mahal biasanya kalau microsecond, millisecond, itu memang mahal. Okay, that one is suitable for power electronics and so on. But for process, the sampling is very large, very high at 60 seconds. One data, after 60 seconds, one data. After 120 seconds, two data, and so on. So to render the simulation realistic, so kita pakai programming, okay. So for the assignment later, I will design something like this, okay. So you have to use MATLAB and Simulink. Have you installed MATLAB software in your laptop?
Yes.
Sudah, semua kena install, So make sure that you have a system ID toolbox in your laptop masa install. So this is the output, okay, from the system, okay, at the F0, okay. So when we combine the input and output in one graph, you can see that figure output try to follow the trend of the PRBS, okay. Nampak ni, kalau dia ke bawah, okay, so dia pun nak ke bawah, tapi lambat lah, dia naik, turun, dia turun, and so on. So try to follow. Okay. So steady state can be determined when the pump stop to flow the input. Okay. So we obtain the readings, all the data. Okay, and then we propose equations. Okay. Kalau dia macam ini, kita panggil dia sebagai absolute value, real value. Okay, yang ini adalah mean value. Kalau ada bar ni mean value. Ini adalah absolute value, real value, and ini adalah mean value for the input and for the output equations. So kita gunakan spectral analysis, which is a plot of power versus frequency to monitor the frequency band implies in the presence of the frequency components. Okay, so this is the power spectrum for the PRBS. Okay, and this one is the power spectrum for the output. Okay, so you can see the strength, which is give the maximum amplitude in power. Okay, so you can see that input power has been packed in a low to middle frequency band. Okay, so this liquid system level system are the low pass filter. Okay, so there is no high frequency, low frequency, meaning that any high frequency fluctuation will be will give a poor response. Okay, so data is been collected 1,500 samples. Okay, so 1,500 samples. So sampling 60 second. Kan? Sampling tadi 60 second. 1 minute kan? So this is the sampling time intervalnya. Okay. So 1,500 samples. So berapa dia punya period eksperimen dia? Eksperimen period. Siapa tahu? Sajalah tanya.
1,500 hours.
Okay. Sample 1,500 samples. From one sample to another sample 60 seconds. So period eksperimen tu berapa?
1,500 darab 60.
1,500 darab 60 kan? Berapa?
90,000 second.
90,000. Okay. Bagi 60 lah. Berapa? Berapa minit?
1,500 hours.
Ha?
Bagi 60 dapat 1,500 balik lah. 1,500 hours.
Bagi 60. Bagi 60. Bagi berapa untuk dapat dalam minit?
1,500 minit.
1,500 minit. Sorry.
1,500 minit. Berapa jam tu?
25 jam.
60. Bagi 60 lagi.
25 jam.
25
25 jam.
Ya.
Wow. Satu hari punya kerja. Is 1 hour punya eksperimen. So, tinggalkan, biarkan dia jalan kan. So kita tidur dulu, makan dulu, sarapan dulu, minum teh dulu, dinner. Habis tu pagi baru datang. So 25 jam punya eksperimen. Sebab dia punya tu adalah 60 saat kan. So panjang lah dia punya eksperimen tu panjang. Sistem ID memang begitu. Kalau dia proses gitu, kalau dia dynamic cepat sikit. Okay. So that's why you partition the data, you dapat 1,500, you kena bagi dua data ni. Okay, 750 for ID and 750 for validation. Okay, so tak boleh pakai semua untuk ID, so kena bagi dua. And then you follow the procedure of the system ID by partitioning the data. Okay, divide by 2, macam saya cakap tadi. So non-parametric models, bila kita nak build up non-parametric models, so kita ada beberapa several important karakteristik yang kita kena pertimbangkan. So now is 10:51. So we have a rest for 15 minutes rest. Boleh? Boleh? 15 minit rehat.
Boleh.
Rehat dulu. Okay. Okay, welcome back to the second part of today's lecture. So previously, I discussed about when you have the data captured along the period of the experimental. So you divide the data into two. One, the first part is for the system ID, and the second part is for the validation. I will do it practically in chapter 5 during a case study, okay, using MATLAB Simulink and real data. So usually before we start using a parametric model, it is highly suggestions from the expert that we try non-parametric models so that we can provide insights into several important deterministic process characteristics with the minimal assumptions. For example, time delay, static gain, and time constant. So this always occurred in the process system under identifications. So time delay we can get by using a simple impulse response or step response, which is known as a classical approach for delay estimation. And then for gain, usually we use a step input, okay, to get the static gain, which is always referred as K, okay, the symbol K. So time delay, usually they use as TD, okay. And then the time constant, usually referred as tau, which is occurred in the system, especially the first order dynamic system, which the definition of time constant is the time occurred when the response reached 63% of the final value step change in the input. So this one also I will discuss in chapter 2, about 1 or 2 hours from now. So the step response naturally suited for estimating these parameters, okay, which can detect integrating effect, and then can detect a settling time for a very large time constant. So impulse response estimate. So this is one of the non-parametric method that we use. So we are using a impulse response estimate by fitting a finite length impulse response using a FIR model, which is using this equation, YK, summation of 0 to n for GL, UK minus L. L is 0, 1, 2, 3, and so on. So this data are using a least square method. So least square method will be discussed in chapter 4. So you can see that the coefficients, okay, G will form the n+1 long impulse sequence, okay, which can detect the delay of these samples to produce the time delay, right? So this is also a popular method as a pre-method or pre-ID for the non-parametric system and parametric system. So at the end of the day, when you inject the impulse response, so you can plot the data, right? So this is the samples of data, 1, 2, 3 sequence, start from 0, 1, 2, 3 until it goes to 30. You can see that if we connected the point, okay, so we will get the output response in the term of line there, okay. So we have about 31 data, okay, 0 to 30, so it's about 31 data all plotted versus time, the amplitude versus time, okay, for the liquid level systems. So you can see that there is estimated falling within the shaded region, okay. This is shaded region, treated as statistically insignificant. So this liquid level system has a unit sample delay, which is a delay in discrete time expressed in terms of samples. So physically, there is no delay between flow and level, i.e. the continuous time system has zero delay. However, the unit delay in the sample data system is due to the presence of a zero order hole. So meaning that when you apply to the discrete time system, you have to sample the system. Every 60 seconds, one sample, 1, 2, 3, 4, 5, until 1,500 samples. So when you use a sample data system, there is a slightly a delay because you are using a discrete time data capture. So this clearly indicate that the sample data still stable, which agrees very well with our physical knowledge of the process. Okay, so this is what I said that start from the 0, 60 seconds, second sample data, 120 seconds, and so on. So this is all the sequence, okay, based on the time base. Then the resulting, what do you call that, square step response, where we inject a step response, so it will give you a data something like this, okay. So you can see that since this is the first data, so there is a slightly time delay there, okay. Can you see that? It didn't start from 0, then it goes up, goes up, goes up, goes up, and goes up. And you achieve the steady state value. Okay, SS is a steady state value. So in this case, it's about, I can say 3.9, I guess. Okay, 3.9. Okay, the steady state error is about 3.9. Okay, so 63% is somewhere here. Okay, meaning that 63 over 100 multiplied by 3.9. 3.9 volt, so will occur the value over here. Then it goes here, then you will get the time delay, with time constant at 63%. More samples, calculation samples will be discussed in chapter 2 shortly, inshallah. So the system approximated as the first order process. The time constant is about 7 samples per minute. In minutes, so the fact that the step response studies out an indicator of the absence of any instabilities and non-stationarities in the process. So the objective in parametric models is to identify a difference equation model for the deterministic process from the given data. So you can guess the time delay, maybe 1 second or 0.1 second and so on. But it's meaningful that the first order difference equation with a delay of 1 unit sample of the deterministic process can be write as this equation xk a1 xk minus 1, which is equal to b1 uk minus 1. Okay, this will describe the true discrete time deterministic response of the process. So let's say the parameters are theta, which is equal to A1 and B1, okay, the transpose. So you can write this one as column vector A1 and B1, okay. So this is a row vector, this is a column vector. Both are same as well. And then the estimated of the sum squared one step ahead prediction errors is minimized. So we minimize the equations between the actual value and the one step ahead value. Okay, and then where we can write it as x hat k minus 1 over a1 x k minus 1 plus b1 uk minus 1 is the prediction of the xk given the knowledge that x and u until the sample of k instant. So, however, this only possible when the true response is known. Okay, since the process, the response still not known, because it will be based on data collection and we based on data plotting. So we just can rewrite as this equation, the output, where yk minus y cap square. And then we minimize the parameters value, which using this function minimum theta. Okay, so you can refer details in book chapter 1 and part 2. So the important thing is the prediction error, which technically known as residuals. Okay, so the residuals is represented by this formula, which is epsilon k yk minus y cap. Okay, so this is the actual value. And this one is the estimated value or prediction value. Estimated, prediction, simulation, okay, approximation, the same word that used in the books. Okay, so the difference between y and y cap, we call it as a residual. The best residual, of course, is the zero value. So a good model should not leave behind residuals, okay, from training. That offers further scope for predictions, okay. That's why you can avoid overfitting as well. So consequently, the following have to be fulfilled. The residual cannot be explained by the input. The residual cannot be predicted using its own path, and the errors in parameters estimate are small or can be ignored relative to the estimation itself. Okay. So let's say we have a predicted value versus observed value. Okay. So predicted value meaning that it is estimations. Okay. Observed value is the value that you observe, meaning that you measure using a sensor. Okay. So this is actual value, okay, observed value by reading, and this one is the estimated value. Okay, estimated value using numerical calculations of the mathematical model. So you can see that we have two model structure. One is output error model. The other one is the equation error model. Output error model and equation error model will be discussed in chapter 3. So I just name it model structure. We use a two model structure. Okay, linear model structure because it's a straight line. Okay, so you can see that the relationship between the observed value and the predicted value is represented by correlations, across correlations. This one is 89%, this one is 94%. Or you can just wrote it as the correlation is 0.89. Okay, and this one is 0.94. Ideal is 1.0. Okay, so ideal is 1.0. So for 1.0, all this what do you call that, the data will be overlapped with the estimated value, with the predicted value. Okay, so in terms of by looking at both graph, okay, of course the output error model structure give the best selections, okay, by indication of the 94% correlations, because the perfect correlation is 1 or 100%. So this one is 94% and this one is 89%. So of course, the output error model structure give the best results compared to the equation error model. Okay, so we look at the zoom. Okay, you can see that this one is much better, where the curve fit almost all the points. Okay, there's a lot of data here. Okay, 1,500 samples of data. So the one step ahead predictions. Okay, sorry. One step ahead predictions from the estimated models are computed on the training data. Then we plot the scatter plot. Okay, prediction versus observed value. Okay, prediction in estimation versus the real value. And then we give the output error give the better results compared to the equation error model. Okay, so based on the correlation percentage, which are higher on the output error model. So we can see that cross correlation function is one of the tools in the system ID where we looking at the similarities between two data. So in this case, the two different data is the prediction value and the observed value, the estimated value and the real value. So that's why cross correlation also important function. Details of it we will go in the chapter 2. So correlation between the residuals and the lag input is plotted here. So you can see that the tolerance, okay, indicate by the line, positive line and negative line. Okay, this is the positive tolerance and this is the negative tolerance. Okay, so as long as the tolerance is small in the band, okay, very small, which is 0.05. So this assumptions of the output error model better than the equation error model is valid because the value of the correlation tolerance is very small. Okay, so we can find the significant correlation as well between the error and the input UK at the positive lag. Okay, and they'll also will be discussed in chapter 2, probably in chapter 2B or 2C. So on the other hand, beside output error model and equation error model, there is another parametric model that also popular, which known as the ARX model. Okay, so ARX model is one of the model that will be used in this subjects, okay, where some of the popular system use the ARX model beside the output error model and equation error model. So this is the correlation between the residuals and the inputs, okay. You can see that there is a word for auto correlations and cross correlations. So always remember that auto correlation is for one data, but correlation, cross correlation is for two different data. Okay. So from there, from the prediction error, we estimate the parameters of the model, which is reported by this table. Parameter estimates error of the best equation error model for the liquid levels. Okay, you can see that we have two methods: the A1 parameter estimate A1, A2, A3, A4, A5, and B1, B2, B3, B4, and B5. So in ID, system ID, this is the, what do you call that? The ultimate results, okay, that we are trying to find, right? The numbers is always changing due to the dynamics of the system, but as long as the error is small, plus minus small, so it is accepted as it is as the nearest model, the equivalent to the real system that offered in the single tank. Okay, so in this case as well, we have to bear in mind that all the ordinary the model is clearly have two respects, which is the parameter estimation error and the parsimony. See the word parsimony here, as I mentioned to you, is one of the keywords in the system ID, which with the minimum parameters with the quality model represent as the nearest equivalent to the real system. On top of that, we also have a test for noise model. Okay, when there is a noise enter to the system. So what we do is we just capture the noise, and then we plot the autocorrelation function. So in this case, as long as it is small tolerance, so we can ignore the noise. Okay, but when there is a tolerance is big, so we have to consider noise as the stochastic part of the model, where it will disturb and it will be significant in the estimated model. Okay, so some of the tests for noise model is shown here. So what we did is we capture the noise data and then we correlate amount itself with the time delay from 0 to 20. And you can see that it's almost 0. The maximum is at 1. Okay, at 1 here. Okay, that is the common autocorrelation for noise. Right, so cross validation. So a good model is one which yields a good predictions. Okay, so in this case we have a prediction of the OE model, output error model, on the test data, which is we choose this one with a correlation of 94%. Then we plot the output, okay, based on the predictions, which is the cross legend, and the observe, which is the line, the black line. Okay, you can see that here. Okay, the observe or the predictions, sorry, the model, okay, try to follow the predicted, okay, as good as possible, right? But this one, it missed this one. Okay, it goes here and then it missed this one, and some of it missed. See? So this is why we cannot get 100% or correlation or 1.0 correlation coefficient, due to the fact that the observed and prediction data cannot fix each other. Okay, so this one is another one. Okay, also same figure. Okay, 2.12 just now. Okay, the same figure. So the predictions. Okay, show some deviation from the steady state and the infinite step ahead predictions. So the cross validation, the formula for it is here. Okay, where it is called as NRMS, or normalized root mean square, which give a formula where y is the actual value, y cap is the prediction value. Okay, the notation here. Okay, modulus dot modulus square stands for the two norm of the vectors. Okay, so the NRMS value for prediction calculate about 72% from the previous example. Okay, so the graph visually confirms the goodness of the predictions. Okay, so at the end of the day, the final model that we get is the first order model. Okay, first order model where yk is equal to xk plus ek. This is the output, this is the input, and this is the disturbance. So the input is entered to here, and then we calculate, then we get the estimated coefficients of A1, which is minus 0.88, and the B1 is 0.4621. In bracket is the tolerance error, okay, for that particular coefficient value. So common practice is to use these equations, okay, where G is the deterministic part, meaning that the process itself, and H is the stochastic part, which is known as the disturbance or uncertainties that enter to the system. Okay, so this is the final model, the output error model in the transfer function form, okay, where the coefficient, we can use this equation to compute in the simulation plus the disturbance, okay. Right. Though we continue with the chapter B, okay, the final chapter in chapter 1, which is the mathematical descriptions of the process models. As we know that model is a set of a linear or non-linear, ordinary or partial differential or difference equations. It involves algebraic equations in terms of the process, okay, variables, states, inputs, and parameters built on the set of assumptions. So there's some terminology, that include in the model, we need to know, because the output did not correspond to the physical output of the system. They have a broader definition about it. Okay, and output always try to predict and explain the input and the noise part in the model. For that reason, the model input are more appropriately known as the explanatory variables. So when we talk about process model, there is a different concept of input-output definitions. Okay, in the term of terminology, for process, this is a real one. Okay, this is based on the experiment. Okay. Okay. Sorry. One B. Okay. So this is a real process, okay, like the single tank just now, where we have the input PRBS, where we have a disturbance, the stochastic effect, and the output measurement. But for a model, it can be parametric and non-parametric model. Okay, so there is no noise on the model. Okay, physical properties. Then we have explanatory variables or regressor and the output. Okay, so model is something that we estimate. Process is something that is real happening in the our environment today. So it highlights the fact that the inputs to the model are not merely the physical input to the process. So the model input is broader set. So it consists of past and present. Okay, so that is important as the data collection will speak the behavior of the process. Okay, and there is so many representation. Either you can use a state space model or transfer function. So I mainly focus on the transfer function because when you go to the state space, it will be much harder. And then some question need to be asked, okay, for the primary classification of model based on the approach that you want to use. Is it you wish the model, do we wish the model to the steady state behavior of the transients behavior, or is it the important process variable dependent on the process direction other than time, or is it the process of interest possess a purely random behavior? And several questions that listed here must be considered so that you can classify the models. So I can say that after we run chapter 1, chapter 1B, and chapter 1A, so models can be categorized or types as first principle and empirical. First principle meaning that based on the derivation, based on the laws of physics and chemistry, compared to empirical, we just capture the input, output, and disturbance, then we construct the model. But bear in mind that the system have a linear and non-linear. For example, for motor, even though DC motor is a linear system, but there is a non-linear factor in that particular DC motor issues. For example, friction, for example, rotations. For example, the heat of the motor will contribute to the non-linear factor of the model. Then there is a time varying and time invariant issues, deterministic and stochastic. Deterministic is something that not including noise, and stochastic is something that including noise. And we are referring to the models that have a single scale and multi-scale. So multi-scale is a big one where you have a lot of single scale inside it. Okay, so it becomes more complicated. And then when it goes to the domain, there is a continuous domain and discrete domain. So usually we use a computer, we must involve in the discrete domain. And we have a static and dynamic process, I told you just now, where dynamics included DC motor, AC motor, something that moving including car, while static is something not moving, that always standing there, like a single tank, double tank, process control. Or it can be alarm and distributed system. Alarm is all together in one system, or can be distributed small system. This is another system and other system. We call it as a distributed system. So this detailed explanation will be in chapter 1, part 3, book chapter that I will send to you. Okay, so model can be classified as approach to modeling, system characteristic, knowledge available to the user, domain of modeling, and response characteristic, which is listed in this particular beautiful picture or illustrations. So as you know that both will do, either first principle or empirical models. Both have disadvantage and advantage. Okay, can be used together. So if you use empirical model in this subject, so we are focusing on the non-parametric and parametric, and black box and gray box. Okay, so no white box. So gray box, we have a few prior knowledge compared to black box that you don't have anything prior knowledge. And both non-parametric and parametric can be used as the strategy. Usually people start with non-parametric, just inject impulse and square and see what happened to the unknown system. And from there, we can know the early behavior of that particular model for us as accumulate as the prior knowledge when we develop the parametric model. And lastly, this is the composite from the model identifications, where you have the deterministic process here. Okay, you inject the physical inputs, PRBS, and then don't forget that in the stochastic part, you have something that noise or uncertainties will come inside and join together, that combined with the deterministic to construct the output, which consists of deterministic and stochastic part. Okay, so some conclusions for model identifications depends on us based on that's why chapter 1 is very important for you to know, even though not much calculation in chapter 1. It's very important to know the concepts, the definitions, the terminology, and some few issues that we need before we go to the chapter 2, 3, and 4 for the rest of the subjects. All right. Any question? Or everybody sleeping?
Okay.
3, 4, 5, 7, 7 students. So we have take a rest about 15 minutes before that, before we enter to the chapter 2 and chapter 2A for today. All right? Is it okay?
Okay, Doctor.
Okay, take 15
Okay,
minutes.
Doctor.
Bismillahirrahmanirrahim. Assalamualaikum and good afternoon. So we continue the lecture by opening the chapter 2A, non-parametric system identification based on transient and frequency response. So as I told you before, impulse signals or unit impulse signals is used as the testing of a system ID as well as step response in order to see the early behavior of the system unknown. Okay, so usually the properties of system impulse response consist of a stable based on the equation shown here. This is a causal, okay, finite or infinite impulse response. It must be linear and it must be time invariant. So this is the sample of the output from the impulse response. So impulse response is a pulse that with a narrow width, okay, that be injected to the system. So we have 3 examples here of system impulse response allows you to determine the certain system properties. For example, causal, stable, and finite impulse response is shown here, yt, xt, 0.5, xt minus 1, 0.25, t minus 2. So you simply can connect the line accordingly, okay, to show the output of the impulse response. Or if the system is causal, stable, but infinite impulse response, so it will be given different output as shown here. And if the system is causal, unstable, infinite impulse response, so it will be bigger, 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 bigger towards infinity, which is not suitable for the system ID cases. So noted that the system response to an arbitrary input signal is completely determined by its response to the unit impulse. So that's why we need to identify a particular linear time invariant system before we can apply to unit impulse signals. Not all systems can accept impulse signals. So how to design impulse signals, how to collect the data, how and to make sure the assumptions are satisfied or linear. So we have some characteristic here. First, the impulse signal should be large magnitude, very large magnitude, okay, magnitude, which is the highest value, and then the small duration unit area, very, very narrow width to produce a good injection system. Then the data collection, the number of impulse tests should be large enough, okay, and the sample period should be short enough. And then the input amplitude must be scaled in order to make the impulse response large compared to the magnitude of the noise signal. So historically, the most popular perturbation is using the step test because it can be easy to generate. Okay, it can enter to any system, not like impulse response, impulse signals. So the most common model structure for industrial plants, okay, is the first order plus the time model, the time delay model. First order FO plus delay time model. So it is the GPS equal to K over tau S plus 1 exponent minus theta S, where K is the static gain, tau is the time constant, theta is the time delay. Okay, so you can use this as the first order model structure with time delays plus time delays. So this is a sample of step test for several plants. Okay, this is for the first order without time delay. Okay, first order without time delay. This one is the first order with time delay. Some book written as date time. Okay, so I don't use date time, so I use time delay. Okay, so this is the time delay, about 4 seconds. And then we have a second order underdamped response. Okay, this is second order underdamped response, and this is the pure integrator when you use a square wave. Higher third order system. Okay, 6S power of 3. And this is a second order system with 0, with inverse response, where you have a 0, it goes down, then it goes up to the steady state value. So in transient analysis, we can use step of impulse. We must record all the output. This transient is convenient for deriving crude models. It can give you information on static gain, time constant, time delay, and it's very sensitive to noise, definitely. Okay, so we will see some examples of first order, second order, and third order system. Okay, so algorithm to derive the mathematical model for this step response is a many method. Yes, one of it is using a method of areas. Okay, method of areas use some steps or procedure as shown here. First, we have to identify the plant gain. Then we have to compute the area A0. Then we have to compute the time A1 area as illustrated in figure 6.5, which is here, A0 and A1, right? So in A1 is indicate the 63% time constant. And then we have to use the remaining parameters for the plant model structure, where time delay is equal to this formula and theta is equal to this formula. Then after that, after we calculate the area, which is here, so we plotted the response. You can see that we have several 4 response here. The first one is the plant. The real data is stated by red. The blue line is stated by the estimated model, which is good, very good. This one is not very good. You can see that the blue line didn't fit the red line, the red data very well. This one also not good. You can see that the blue line cannot fit the second order response with time delay very well. And this one as well, the blue line cannot fit the red data as shown here. So the best response is this one. Okay, it looks very good, very acceptable, and can be further processed for the controller steps. Okay, but sometimes you have outliers, right? So outliers is shown here. Okay, suddenly there is a data which is not in the cluster of the red data. Okay, so this must be deleted from the data. It's considered as the outliers. Okay, so that you can have the good results compared to the others. So I give you examples. So in these examples, we have to, describe what is the mathematical model of the system. Okay, so shall I use iPad to describe it? So I share with iPad first the response. Okay, so you have a okay, T, and then you have a response there, right? This is your CLT. This is the time. Okay, so we have to find the mathematical model of the first order system. Okay, right? So this is a first order system, first order. Okay, no time delay because it starts from 0, right? So it's a first order system, and structured given by GS K S plus tau. Okay, so that is the model structure for the system. So if we go to the system there, right? So the input is a unit step. Okay, so the transfer function can be determined by measuring the time constant from the graph, and the time constant at 63% of the final value at t 0.0244 seconds. Okay, so if we go to the plot, okay. Okay, yeah, so 63% is somewhere here, 63 for time constant, multiplied by 2. 2 is the steady state value, right? So this one will give you the value is about berapa tadi? 0.0244 itu adalah time constant dia. Jadi kalau kita pakai calculator, (63) 63 divided by 100 multiplied by 2 volt. So it is 1.26 volt. So 1.26 volt is somewhere here. And it goes to here, which is the time constant. The time constant is from the graph is 0.0244, if I'm not mistaken. Okay. Okay, 0.0244 seconds. Right. So we estimate the first order, okay, which is the first order model structure. G is equal to K S plus A, where A is equal to 1 over tau. Okay. Right. So A is 1 over tau. Tau is 0.0244, which give you 40.9, the value of the A. Okay, and then the final value or steady state value, okay, is equal to K divided by A, which is equal to 2. So that's why you get K is equal to 81.967. Okay. Okay. So G is equal to K over S plus A. A is 1 over time constant, tau. So A is 1 over 0.0244, which will give you the post value, 40.9. So the final value or steady state, SS is steady state, is over K divided by A, which is equal to 2. So that's why it's 81.967. So in that case, GS 81.967 over S plus A. A is 40.9. Okay, is the estimated for the estimation for the data plotted as the first order system. So this one, if you draw it, okay, so it's located at here. 40.9 is the first order system. First order system definition is a system which have what do you call that? One pole. Okay. So how to plot the response using MATLAB? So is very simple actually. So you take these equations. Okay, this is the numerator, and this is the denominator. So you use a MATLAB. First you wrote as 81.97. Then denominator 140.9. Then step. Okay, step which equals to numerator denominator. Okay. It is good if we can what do you call that, show it in the computer. Okay, shall I show you if you don't mind? Okay, so we open the MATLAB. Okay, VPN UTM. Okay, so it's a license. You go to the password. Okay. So go to the service admin. Okay, MATLAB. Is there any MATLAB here? I hope can. Okay, so you just run the MATLAB software. Is there any software MATLAB in my computer? Applications. MATLAB. Okay, I'm sorry, my MATLAB is not in the desktop anyway, so no worries about it. I will show you later in the second half of the lecture. So if we go to here, we plot it as a, so you can get this kind of response. Okay, is the first order response. Okay, there you go. This is for the rise time. This is for the settling time, and for the time constants is somewhere there, which is 1.26. 1.26 is something weird. Okay, so it goes here, time constant. Okay, this is a 1.26, 63% from the 2.0. Okay, so you will get a time constant over there. Okay, then you compare between the data, the real data, and the estimated model. Okay, it's good for you if you can plot both graphs in one plot so that you can see the difference. I will show you later in the next slides. So example 2 is one of the second order identifications based on time response. So all data are collected. Okay, data are collected and plotted. Okay, data collected and plotted. Okay, collected and plotted. Okay, as shown here. Okay, so you can see that the response there. Okay, so I just wrote in my iPad first. Okay. So first we must find some information from this plotting. Okay, so what you should do is you have to determine what you can see from here is the maximum amplitude. Okay, C max. Then this one, C steady state. Okay. What else? Can say as the settling time over here. Okay, settling time. Right. So if you get that value, so you can start construct the model. Okay. So from the graph, the C maximum. Okay, C maximum here is 13.82. Of course, it must be plotted in the real scale graph. Then the C steady state or C final is 11.03. Okay, and the settling time is 2.62 seconds. Okay, so you calculate the overshoot percentage. Okay, so overshoot percentage is C maximum minus C steady state divided by C steady state multiplied by 100%. So you will get 25.3%. Okay, you just insert the value of C max, CSS, and CSS as here. Okay, then you get 25%, 25.3%. Then estimate the second order system, which is the damping ratio is equal to 0.4. So you have two important parameters here, which is zeta. Zeta is a damping ratio, and omega n, which is the undamped natural frequency, right, at 3.82. So zeta is 0.4, omega n is 3.82 radian per second. So how you get the zeta? So zeta is from the formula, which is listed here. Okay, so just insert the 25.3. Okay, 25.3 you insert here, then you insert here, then you use your calculator. This is ln. Ln is natural logarithm. Okay, log natural. Okay, log base e. Okay, ln is log base e. Okay, so settling time formula is 4 divided by zeta omega n, right? So from here you already know the settling time, which is settling time is 2.62. So 2.62, then zeta is 0.4, then you can get the omega n value 3.82. And then the C final, okay, C steady state is equal to 11.03, which is equal to K divided by omega n squared. This is the formula how to calculate the static gate. So K is equal to omega n squared multiplied by 11.03, so you get 160.95. Then you insert the K value, okay? Insert the K value, you insert the zeta value, omega n value, and omega n squared value. Finally, you get the mathematical model for the second order transfer functions. Okay. So this is the mathematical model, 160.95 divided by s squared plus 3 plus 14.59. Okay. So go to the Okay. So the MATLAB is numerator, double prompt, how to write MATLAB program, 160.95. Double prompt, enter, double prompt, denominator. 1, because the coefficient of S square is 1, space 3.056 and 14.59. Then just call the function step, which is equal to, and you press enter. So once you press enter, you will get the answer, which is yeah, okay. So you can see here 25.4, which is same overshoots, same settling time, same steady state value, and the rise time, of course. Okay, you can use it to produce the MATLAB graphic, and then you compare with the real data. Okay, which is almost the same in terms of scale. In terms of scale. Example 3 is all about the same, but now it's given a peak time. Okay, you are given a peak time 4 seconds. Okay, so peak time is over here. So this is your peak time. Okay, at C maximum. The C maximum is about 1.4. And the C steady state is equal to 1, right? And you can use either peak time or either settling time. Both will do. So now we change our strategy. We use a peak time instead of settling time. So from the graph, you can see that the Cmax is 1.4. So steady state is 1.0 divided by 1.0 steady state, and the overshoot is 40%. Okay. Overshoot is 40%, and this 40% will go to the formula of zeta, okay, to calculate the zeta, which is 0.28. So you will get the answer 0.28. Then use the peak time formula, which is pi divided by omega n square root 1 minus zeta square over 4 seconds. 4 seconds is given. So just change the formula title, omega n, then you will get omega n 0.818 radian per second. So the final value is equal to k divided by omega n squared, which is the static gain error. Static gain k. Okay, so k is equal to 0.669. Okay, so substitute all values. So you will get 0.669 divided by s squared 0.458 s plus 0.669. Okay, so that is the final transfer function, and we plot using MATLAB. We get the same answer as before and compare with the data, which is the equivalent in terms of the shape and plotting. So this one is the another examples. You are given peak amplitude C maximum 1.25, overshoot 25%. Okay, the time is peak time is 9.96 millisecond. Okay, 0.0096. Then the settling time is 0.0245. So some solution of it, so you will get more or less same as before. 117916 is the second order system. So example 5, this is the data from real data response, which is the green one, and the blue one is the estimated, okay, or simulated, okay. So you can see that when it plot together, okay, you can see that the blue one try to curve it as close as possible with the real one, the green. And this is the mathematical model, 20.17 exponent time delay, which is 0.5 second over S squared plus 3.631 plus 20.17. But this is not a good predictions. And then try the other data from other students. You can see that the blue line can fit the green line very well, okay? Which is considered as accepted. This one is not accepted. This one is accepted. And this one, the third one from the third students. So you can also similar like the second students, the mathematical model. So this one is accepted because the estimated close to the real values of green. Okay, and then more example, you can click this link and play around, okay, and get some data from the my website. Once you get the data, you can plot, or otherwise, if you don't have the experiment, you can generate it. You can generate the transfer function by using this computer program that I give to you for your time to play using a MATLAB, right? So some exercise for you to try, okay, after the lecture, okay. This one also, okay, some exercise for you to test. So the second part of it is the frequency response identification. So the frequency response identification is the simplest way where you experiment the plant using an input series of pure sine wave. Okay, you can use it by experiment, but it takes a lot of time, 2 hours to 3 hours, or simply you can use the Simulink block diagram, okay, as I shown here. So let's say we have a 12 sine wave, okay, tested from 0.2 to 6 radian per second, and we plot it, okay, with a different frequency, omega 0.2, 0.3, 0.5 until 6.0. What is your observations? At the early stage of the initial frequency, the diagram of the input and output is almost the same in terms of magnitude and phase. But when it goes to the 6.0, you can see that the amplitude is reduced compared to the input, and there is a phase difference, okay, among the data of input and output. So that's why we captured the input here, right? The input derived from the laboratory data. So you can see that we vary the frequency from 0.2 to 6.0. Then we capture the amplitude ratio. Amplitude ratio actually is a V0 over Vin. Okay. So from here, we use 20 log V0 over Vin to get the decibel value. Then we capture the phase degree. So how are we going to capture the phase degrees? Because the phase degrees have negative and positive value. When it will become positive and when it will become negative. Okay, so I show you here how to differentiate between the negative and the positive value of the phase shift, because some of the data that we have a positive value phase shift. Okay, so let's say you have a data here, which is time. Okay, input and output voltage. Okay, so we begin with the input. This is your input, sine wave. And this is your output. Okay. And then, so we see it from the oscilloscope or from the plot. Then we mark here the difference between input and output, which is X. So this is your input, and this is your output. Okay. So X is the difference between phase and between the input and the output. And the other one is the one cycle of input is Y. Okay, one cycle of input. So phase shift is equal to X divided by Y multiply 360 degrees or 2 pi. Okay, so it can be negative, it can be positive. So if negative is when input leading output, okay, you get negative. But if the positive phase shift when output leading input, okay. So you have to understand this concept first, because maybe I will ask when the phase shift become negative, when the phase shift become positive, right? Okay, okay, eh? Right. So come back to the slides, okay? Where now, if you see that, oh sorry. Okay. Now, if you see that all our data here, phase shift is negative. So meaning that the input signals is leading the output signals. That's why the phase shift is negative. Right, so the frequency response conceptually simple, okay? Sine wave approach is not efficient for non-practical, but some researcher while attempting a frequency response characterization for the some system, it's difficult to produce a good quality sine wave, okay, when the plant using the control valve especially. So in addition to that, since the range of frequency span over 3.5 orders of magnitude, 0.001 to 3 radian per second, the testing time was extensive, quite long. Okay, so that's why we, but anyway, in other systems, for example, for XY milling machine, it's good to use a frequency response. But if the system have a control valve, okay, on and off, open slowly from 0% to 100%, it might have some problems. Okay, so we plot it. Plot is based on the magnitude and phase versus frequency, semi-log, okay, logarithm frequency. Okay, so this is some of the example of the first order system, okay, where you need to understand the basic factor in workload that you learn during, what do you call it, during your undergraduate. If you don't understand, I will give you a book chapter on the frequency response for you to review and to revise back again. That is the first principle where you are given a state transfer function, you plot the workload. There is a last subchapter of that book chapter where you it explain experimentally driven transfer function based on sine wave testing. So I give you some review from the books, okay, for the constant workload for magnitude and degree phase versus semi-log, okay, and then first order, sorry, what do you call that, derivative S and derivative square, okay, then integrator and square integrator response, and then some first order zeros, first order poles, okay, and second order plotting of workload, okay, until the higher order, which is the fourth order, for you to review, okay. And this is one of the good example where you have a workload second order with time delay. Okay? This is a conveyor belt with tank. You can see that the conveyor belt with tank, where the conveyor have a time delay. The tank is a integrator that is with the 0 on the top, and then this is the process. Example. So for tests and examinations, we are not required you all to plot the data. The data is given and we plotted for you using a scale. Then you have to use that particular graphic to extract out the information to construct the mathematical model. Okay, for example, in this case, you are given frequency response data. Okay, and then you have to derive the mathematical model. You can see that the data start from 6.15 decibel. Okay, and then it goes down. Okay, with the slope of minus 40 decibel per decade. And the phase is start from 0 degree, goes to minus 100, it goes to minus 180, then it fall down under minus 180 degrees. So referring to the amplitude graph, the asymptotes have been plotted and deduced that the gain at low frequency is constant at 6.15 decibel. Okay, so from there, we know that the system is type 0. Okay. Type 0, okay, because there is no slope of minus 20 and minus 40. So if there is a slope of minus 20, so it is a type 1. If there is a slope of minus 40, so meaning that it is a type 2. Okay, so this frequency response have a minus 40 decibel per decade, meaning that the system is second order system. Okay. If minus 20 decibel is a first order system. If the slope minus 40 decibel, there is a second order system. The slope that I mean is this slope. Okay, minus 40 dB per decade. Okay. So the transfer function model structure for the second order system is given by k omega n square over s square plus 2 zeta omega n s plus omega n square. So the undamped natural frequency is obtained from the asymptote intersection, which is a 5 radian per second, which is located over here. Okay. So if we plot it, this is 10 power of 0, 1. This is 2, 3, 4, and 5. So when we go up, okay, the cutoff is here, okay, where the omega n value occurred, which is at omega n 5 radian per second. Okay, K is obtained from the low frequency gain, which is 20 log K equal to 6.15. So K is using anti-log. Anti-log 6.15 divided by 20, which is equal to 2.03. Damping ratio zeta is obtained by comparing this magnitude curve versus frequency with the standard second order system curve, which is here. So this is a standard second order curve, which have a different value of zeta, right? So it starts from here, 0.05 until 1.0. So when we compare it, it is observed that the system have okay, standard second order. So it is compared that the corner error is minus 1.55 dB, which propose that the undamped natural frequency is 4.6 decibel or 1.7. Okay, so approximately the damping ratio is 0.6. So once you know the damping ratio 0.6, you enter the 1.7 value and the 0.6 inside this model structure, then you will get 50.75 divided by S squared, 6S plus 25. Right, how to plot the boat plot? Okay, using a MATLAB. So you should try like this. So based on the 50.75 over S squared, so you just write like this, 50.75 denominator 1, 6, 25, then both numerator or denominator. Okay, so I share the computer program with you. Okay, 50.75 denominator 1, 6, 25, then both is numerator, denominator, then you can see that the boat plot will come with the magnitude and phase in one graph. Okay. So you can see that when you compare the data and the model, this is the real data that we get, and this is the model. You can see that the model flattened, the phase flattened at minus 180 degrees, but this one is not flattened at minus 180 degrees, meaning that the system have a time delay. So that's why we have to include the time delay, about 1 second in the model structure, so that you can find the exactly predicted, which is equal to the real value. Okay. So the next examples, you are given a data where frequency, output voltage, and phase shift. So you can see that here, this data is V0. Okay, the input is constant, 5 volt from the beginning of the frequency till the end. And you can see that is a positive and negative, okay, meaning that when the experimental is on run, the output is leading the input, produce a positive phase shift, while the input leading the output, it produces a negative phase shift in degrees. So what we should do is we take a ratio here. This one is a ratio, V0 over V in, okay. Then the gain is 20 log V0 over V in, okay. Then you get the value of decibel. Then you plot it, so you can see that the cross legend is the real data, and the straight line is the line that fit the data. Okay, so we have a two slope here. One is positive 20 dB per decade, meaning that there is 1 0 in the model, negative minus 20 decibel per decade, meaning that there is one pulse in the transfer function, and there is a two corner frequency, which is at here and at here, which is at 0.1 and here 11 is about 20 radian per second, 10, 20, 30 until 100. Okay, and the phase here, okay, is the plot. So now initially the board gain plot has a slope of plus 20 decibel per decade, and the phase plot shows a constant phase shift of 90 degrees. So there is a zeros at s equal to 0. Two corner frequency 0.1 and 20 that I mentioned just now. So both cases, the gain plot changes slope by 20 dB per decade. And then the both gain plot has a final slope at minus 20 dB per decade. Okay, not 10 to minus 90 degree. So it suggests that the system has one more pole than zeros. So suggests there is some time delays in the equation. So the model structure will be like this. G is equal Ks over zeros, poles and 2 poles, okay, which is occurred at 0.1 and 20 radian per second corner frequency. Then we calculate the gain K using this magnitude formula, okay. Then we obtain the K value, so, okay, K value which is at about 16, okay, at 1 radian per second we insert the frequency value. And the transfer function will be 16s 1 over 10s 1 plus 0.05s. So since the time delay is equal to 0.01 second, so we include the exponent factor which represent the time delay of the system. And I give you a sample of program to generate a frequency response data using MATLAB, which you can try later on. Okay. So some example for you to do during weekend and during next class, which is will be held inshallah in 19 December before Christmas. Okay, so I think you can glance through some of the examples. Okay, so I leave it to you to test it. Okay. So I think it's 1 o'clock already, so I will stop here. Okay, so I will continue again 19 December. Any question from the students? Everybody okay?
Doctor, in case I have a problem, I can just ask in the WhatsApp.
Can ask directly
Oh,
in WhatsApp. Can direct us
okay.
in WhatsApp. Okay, I try my best to assist you during the online study. So the test will be on the 19th or 20th December, first test lah. Okay, so we will do the test online, and I will during the test the camera must be on lah. During lecture, no need to on your camera, but during lecture you have to on your camera and off your microphone. Okay, is it okay? Have you have experience using online test before?
No, never.
Never. So I will use a learning platform. I will inform from time to time. Okay. So we begin with the what do you call that, full-time test one next week. Okay. And then the part-time will be next month. Of course, the set question will be different, but in the same scope. So the scope will be chapter 1 until today's lecture. Until today's lecture, okay? The scope of the test 1. So if there is no question, I will end the class, okay? And I see you next month, okay?
Alright.
All right. Thank you very much.
Thank you.
Thank you.
Yes, thank you.